without you. Falling in love with the same old drug. I'm drifting away, drifting into. Got to get high to get by without you. Got to say to myself, simply got to say to myself, simply falling apart with a broken heart. I'm drifting away, drifting into. Got to get high to get by without you. Got to get high to get by without you. Got to get high to get by without you. Got to get high to get by without you. Got to get high to get by without you. Got to get high to get by.
All right. Hi, guys. So, midterm 2. Reminder, that's still on the 20th of March in various rooms. And again, the way to study. What I strongly recommend is especially the lectures starting from this week. These guides have been through a lot. They got a lot of problems. There's a lot of things to think about. You can click here. You can work on these problems. And, importantly, argue with your friends about them. So, why does this problem work the way it does? I think those are all great things to do. Yeah. Which one? Here? Section. What section? Holding? There's some word I'm missing. Yeah. Sorry, it's like across the room it's hard. L-E. LT. LT? Ampersand LT. Got it. Oh, that. Oh, thank you. All right. Was it worth it? Who knows? All right. Got it. Okay. Sounds good. We just moved to a new system for displaying these. It'll be fixed. Good. All right. The key thing I don't want you to do is look at old exams and then think about it a little bit and then go look at the solution and then say, now I understand, because you have understood probably not that much. The real thing is thinking about your process and really struggling and then arguing and asking each other weird questions. Okay? Again, I'm such a big fan. All right, moving on. Hashing. So today we're going to talk about the cousin of the binary search tree, and it's a really, really cool idea. It's super slick, and it feels like cheating, And yet, it's the underlying data structure, or the underlying idea that drives quite a lot of stuff. So hashing is important not just for hash tables, which we'll talk about today, but it's also very useful in cryptography. So there's things called MD5 hashes. We won't talk about them today. It's also really useful in the way that Git works. So Git relies on hashing in really important ways. It's a really important, universal, wonderful idea. Okay. So recall that last time, actually 2 lectures ago, we talked about the idea of an ordered linked list and how you could technically use it to build, say, a set that has a contains and an insert method. Okay? And a linked list based set would have very slow contains and insert runtimes because we would need to iterate through our list potentially. Okay? Now, an alternate way of doing things, we said last time, was what if instead we made a tree-like structure, and in that case, our contains and our insert operations would be very fast in the worst case, as long as the tree was bushy. That was the punchline of the last 2 lectures. Now, we did talk about some extra stuff about how do you make sure the tree's bushy. That's where 2-3 trees and red-black trees came in. But fundamentally, the most important thing is if you have a balanced tree-like structure, your operations are very fast for a set implementation. Okay? Now, there's some limitations, right? One is that the items need to be comparable in some way. So in this case, I have letters, and they have a natural ordering. But maybe you want to store a set of other things that don't have a natural order, like pictures of me or whatever, right? In that case, it's not clear which picture of me is less than another. Maintaining bushiness is not easy, so we have to return to some kind of clever tricks, and we had a whole lecture about that. And even in almost an hour, we weren't really able to close the loop all the way and do all the bushy tree stuff, right? I said there's an optional section where we talk about rotations for maintaining the isometry, and so it was a non-trivial task. Now, there's also another maybe arguable limitation. A while back, I said that log is really good, so the fact that binary search is log was wonderful. Now the question is, could we actually do better? Like, could we somehow do, I don't know, constant time? And so what we're going to see today is that we can do better, intriguingly. Now, again, the practical runtime difference is very small. Log's pretty good. Like, if you have 1 billion items, you still have a tree that's only height around 30. So that's pretty good. But we're going to try and do better anyway, because 1's better than 30. Okay? So here's an alternate approach. Similar to with weighted quick union, where we took a step backwards for a moment. This will eventually take us further. So imagine we have a set where we implement it using an unordered array. So if we want to know, does this data structure contain something? What do we need to do with this array? Potentially. Like, I want to know, does this array contain Q? What do I do? I look through the whole thing. Okay, so that's going to be slow. It's going to take n time to do contains, and it's also going to take potentially n time to do insert, okay, in the worst case. So, not a very good data structure, right? Bushy BSTs are better. Unordered arrays are clearly worse. But we could do something we'll do in a moment that's pretty sneaky, where we can make our unordered array faster. Okay? So one really extreme approach, something we could technically do, is observe that all data is really just bits. Now, this isn't something we've talked about on a deep philosophical level, but you will in 61C. But it turns out integers, that's just a sequence of bits. Or a string, that's just a sequence of bits. Or even just a picture of anything, a horse, let's say. A horse picture is just a sequence of bits. And so what you could do is create a gigantic array that has for each element, is that item in the set or not? Okay. So for example, we say, like the most obvious way to do this is, let's say we have a set of integers, all right? What we do is in location 0, this will call it a data indexed integer set. And once I create one of these things, if I insert 0, that means I just have this giant array and I set 0, item 0 to true. So this is an array of booleans. And then I set item 5 to true whenever someone says insert 5 and so forth. So it's a set where we have a specific location that stores the trueness or falseness of that item. And so hopefully it makes sense how you can store integers in this thing. And because data is just bits, we could technically play the same trick with anything. Like a string is ultimately, you can represent it as a number and then set true. So if I have, horse, again, to use that favorite word of mine, you would compute the integer that corresponds to horse, and you would just set it equal to true. Okay, so any questions about this idea? So it's sort of cheating, right? That's how I'm going to say you insert. I just set a Boolean to true. So there's some major downsides of this approach. Actually, first I guess I should ask, how fast is insert going to be? Constant time. You're just setting an array element to true. And contains, how do you do that? We just check the element, and that's going to be constant time. It doesn't matter how many trues there are, contains will be quick. So there's some downsides, though. One is it's extremely wasteful of memory. So just to check all positive integers, we would need to make an array of 2 billion integers, 2 billion booleans that are all going to be initially false, and we'll just set a handful of them to true. So that's pretty bad. And then another thing is, while I kind of alluded vaguely that one day you'll take 61C and you'll be able to turn horse into a number, we need some way to do that in a more concrete way than just saying you'll learn about it in 61C. Okay? So this is the idea that we're going to build on, and hopefully you agree that it's super fast, although it has these downsides. Okay? Now the implementation, it turns out, unlike binary search trees, which are a huge pain to implement properly, this is so trivial. Like literally all the code is when you create a data indexed integer set, you create a Boolean of some length, whatever the biggest number you want to support is. So in this case, only 16. When you insert, you say the item that's present is true. And if you want to know if it's there, you just return present I. That's it. Now, this again, the limitation here is it only captures numbers up to 16, and you don't do anything like resizing. It's not like it gets full, and then you need to resize. Here, we're literally just only tracking the presence of numbers 0 to 16. Any questions about this? All right. So that's the key idea. And hopefully you agree this is like the dumbest, but the fastest and the smartest way to implement a set. Okay? So this approach, it actually has a runtime of theta 1. And let's say you don't like 16. You want to support more numbers, you just make this bigger. And the more space you use, the bigger the set of numbers you could possibly store. So we're cheating by exploiting space to save time. It's kind of like memoization. It's in that flavor of thing, right? And so by doing this, my runtimes are now theta 1. Good. Now we have the limitations we mentioned, which is, again, I can only look at the numbers from 0 to 99,999, but it works up to that. So we'll try and do better in a moment. Okay, so let's suppose we want to try and start addressing these issues, and let's say we want to insert the word cat. What do we do? Okay. Well, the key question is, what is the cat element of an array? Like, what is that? How do you know where cat is? And so one idea would be, let's just use the first letter of the word as an index. So in this case, I'll think of 0 as never used, 1 as A, 2 as B, 3 as C, and 4 as D. Okay? And in that case, when someone inserts cat, I'll just set this to true. Now there's some issues with this. One is that 0 never changes, so that was just a wasted piece of space. And there's other issues, like, for example, that, well, we have a clear collision, is the word we'll use. So when we say, does this contain chupacabra? The answer would be yes, because we look at 3 and we see that it's true. Another issue is we can't store strings that don't start with letters. Like, what would equal be? There's no equal character, at least the way that I'm describing it here, where 1's A, 2 is B, and so forth. But hopefully you can see that it's moving in the right direction, although it also seems like cheating. But we're getting there. Okay? So that's it. We're just going to use the first letter. Okay? Here's an even better approach. Rather than just using the first letter, let's use more letters. So in this case, let's treat each digit in this, or each character in the string as a number in a base, or sorry, as a digit in a base 27 number. So in other words, okay, so bear with me here. C is the third letter of the alphabet, A is the first letter of the alphabet, and T is the 20th letter of the alphabet. And so the index of cat will be 3 times 27 squared, plus 1 times 27, plus 20. So you have some gut feeling that this should result in something roughly unique, maybe, because it's a base 27 number. We're getting a little mathy, but I'm assuming that's fine. And so this index here, this right here, the number I get back is 2,234. So this is cat. We've turned cat into this particular number. Okay, so why this specific pattern? Like, why does this seem like a good idea? Well, let me take you guys on a trip down memory lane. Let's talk about decimal numbers, okay, which you guys hopefully all know, unless you're from some, I don't know. Anybody here like an ancient Sumerian who's come forward in time? Uses base 60? No? Okay, good. So in base 10, the way it works is we have 10 digits. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Perhaps you've heard of them. If you want numbers larger than 9, the trick that someone came up with, very clever, much better than the old Roman way of doing things, is we'll use a sequence of digits. So for example, 7,091 in base 10 is 7 times 10 to the third, plus 0 times 10 squared, plus 9 times 10 to the first, plus 1 times 10 to the 0th. So that's what this interpretation, like, you know, you don't think about it anymore, but at some point you did. This number in base 10 is this expansion of this sum, right? Sums of multiples of powers of 10. Okay? So if we were to go all the way down to, and getting a little bit of a 61C preview here, but if we were to think about not just base 10, but other bases, let's say base 8 and base 2, we can see that for every number in any base, there's the base 10 equivalent that we're going to be thinking about natively as humans who have 10 fingers. Okay? And it'll all come back together. We'll talk about cat some more in a minute, but just some review here. In the binary number system, there's only 2 digits. Okay? So we had 27 base 27 earlier, then base 10. We're going all the way to the bottom and having just base 2. I guess you can also do base 1, but that's a really boring base. So in the binary number system, we have 2 digits, 0 and 1. And if you want numbers larger than 1, you have to use a sequence of digits. Same idea, right? You want bigger than 9, you got to use a sequence of digits. So I have 0, 1, that's too big, so I roll over to 1, 0, 1, 1, okay, and then I go to 1, 0, 0, and so forth. And each of these binary sequence of digits is just like our friend in base 10, and here's base 8 just for fun. So for example, let's say we take the number 1110, base 2 and base 10. What is that going to be? Well, it's just going to be the sums of powers of 2. So 1110, base 2 is 1 times 2 to the third plus 1 times 2 squared plus 1 times 2 plus 0 times 2 to the 0, right? So this whole thing ends up being 14. Now, what does that have to do with cats? We'll get there in a minute. Okay, so if it seems like we've just gone on some random detour into binary, it'll connect in a moment. But what we've got here is just saying, hey, for every binary number, there's the equivalent base 10 version. Okay, so you guys agree with me that this is 14? Hopefully. All right. So we can keep going with this. And we could say, let's say we have a 32-bit binary number. Okay, so here's a big old binary number, has 32 bits, kind of like integers in Java, by the way. What is this number going to be? If we wanted to interpret it as humans, how do we do that? Well, each of these says we want to sum these particular powers of 2. So we have 2 squared, 2 to the 4th, 2 to the 5th, 2 to the 10th, 2 to the 11th. So if we sum all those together, we will get, in this case, we expand it out, and we get 3,124. So this particular sequence of bits is the number 3,124. Okay. So this brings us back to cat. Okay. So in Java, whenever we decide that cat is going to be 3 times 27 squared plus 1 times 27 plus 20, we get the number 2,234. Okay? And we can, just like we could convert a base 2 number to base 10, we can convert, in this case, I guess you could think of it as a base 27 number to base 10. And we can also look at it in binary. So this is all those together. So this is the base 27 representation. This is the base 10 representation right here. And here's the base 2 representation. Okay? I find it useful to think about the base 2 representation because at the end of the day, this is what the computer is doing. This is how it's storing your bits. So when you say the word cat, that's the thing we're going to set equal to true. We're basically saying this sequence of bits represents cat. Okay? In base 32, another approach here that you could do, okay, so that was, this approach we had before was, because there's only 26 letters to the alphabet, it's convenient to use base 27. But I argue that it is even nicer, okay, and this is why all the binary stuff mattered, that it seemed to be kind of a sidetrack, is that if we use base 32 instead, because of the special relationship because it's a power of 2, what we could do is, in this case, in base 32, okay, so if I think of cat as 3 times 32 squared, plus 1 times 32, because this is the letter A, plus 20, and get 3,124. In this case, each letter is exactly 5 bits. Okay, it's good for lecture, because at this point, we can easily see that this cluster of 5 bits corresponds to the T, this to the A, and this to the C. I hope that made sense. Maybe I will revise that. Felt a little long for a simple point. So the point here, though, I think, is the number we use to represent cat is arbitrary. Okay, one possibility was treating it like a base 27 number, and we get 2,234. Another just alternate approach is base 32, in which case we get 3,124, and both representations are fine. We pick it arbitrarily, but I'm going to use this one now because it has an easy interpretation. There's these 5 bits for T, these for A, these for C. All right, that was quite a lot of stuff. So any questions about this? So all of that was just to say how we represent cat was kind of arbitrary, yeah. So what's with all these zeros? Okay, great question. So in Java, we have integers, and remember how we're storing everything in our data index set is we're using an integer index, right? And so an integer in Java is 32 bits, and this is 5, 10, 15, 20, 25, 30, 32. So in a sense, these are all set to 0. Yeah. So the good point is brought up here, which is if we go longer than 6 letters, we're going to roll off the end of this and it won't seem to work. And we'll address that towards the end, but it's a limitation of our approach, yeah. So it's better than before, but still not perfect. Okay. So in this case, if we use base 32, the data index set will set the 3,124th item equal to true. Okay. And just by the way, in case you were curious, why is it that we get 5 bits exactly for base 32? Well, it's because if you multiply by 32, it's equivalent to shifting over by 5 places. Okay? So you just think of this. 5 bits equals 32 bits. Maybe that's a simpler way of putting it. Okay. So now let me bring it all together and imagine what it's like to try and store multiple words like cat, dog, potato, and snack. Okay? So what we'll do is, as on the previous slide, let's use 5 bits per letter. Cat ends up being 3,124. Dog in base 32 would be 4,583. Potato would be the set of a much bigger number. And so ultimately our data index set, it's an array 2 billion long, and we set 4 elements to true, and that says we have stored cat, dog, potato, and snack. Okay? All right, thoughts on this? Yeah. How do you get it back? Okay, well, if we wanted to, the 2 operations we care about are put and contains. And so you'd say, hey, does this set contain dog? And then you would just compute this number again and then check if it's true or false. Now, if the question is which items are there, then we would need to iterate through and figure out how to convert this number back, which you can do. Yeah, but good point. And we'll address that in a simpler way in a little while. Yeah. So if it's long, we're screwed. All right, we'll fix it though. Good point, right? So we're just like kind of building on a simple idea and make it better and better, and we still haven't got a perfect idea yet. So what about longer strings? Well, you either have to tolerate a maximum string where you can say, sorry, you can't store strings longer than 6, or you have ambiguity. So the example that I computed by writing a script to find words for me that mapped were hothead and pothead randomly, so great. And so in this case, they're both represented by this number, and so we don't know which one we have. Is this hothead, pothead, hothead? Who knows? And that's because P and H have zeros on their far right side, if you count out what number they are. Now you might say, well, if we do base 27, then we get a little more room, but it obviously won't save us, right? We need even more than that. Okay? All right. So let's see what this would look like. So yes, for now it doesn't work because we have this issue with long strings, but it's actually not such a difficult algorithm to implement, given its limitations. When we insert, we convert our number to a string. We take our string and convert it to an integer, and then we set that item to true, and then we want to check if we contain it. Same deal. We convert it to an integer using our magic function, and then we see, is it present? Okay? All right. So what we could imagine doing then, if you want to know what convert to int looks like, this is code that I don't want you to look at too closely, but it turns out to not be so bad to write it out. Right here, this code says the integer representation is initially 0. For each character in the string, we're going to take the current representation and multiply by 32, which is the same thing as shifting by 5. So I use this new operation you've probably never seen. And then we add the next letter. So you could think about it later, but it turns out this does exactly what we've been describing in lecture. And then letter num just gets back the letter we care about. Okay? And we throw an exception if you give me something that's not a letter. So that's one of my rules. All right. And letter num, remember what this is supposed to do. I didn't say it out loud, but z is supposed to be 26, a is 1, and this is a function that just does that. And this is just to prove to you it's not so bad, but I don't want you to digest this code completely. Okay. So we have 2 fundamental challenges that we must address before this is not something that's useless, right? It's cute, but right now useless. So the first issue is how do we resolve ambiguity? Gross pi versus boss pi, right? If you get a pi, you want to know if it's gross or totally boss. And we'll call that collision handling. And then the other is, well, more generally, is there a better strategy for taking arbitrary data and getting back an index? And we'll call this computing a hash code. Okay? Now for strings, this was easy. We treat it as a base 27 or a base 32 number. Or it was straightforward, rather. It might not be easy. You might need to go back and think about that again later. And an important point is that Java, actually, this is something that's considered so important to the Java programming language that every object is supposed to provide a hash code method. It's a way of taking an arbitrary thing, like a string or a tree or a game or a tile, a TE tile or whatever, and you're supposed to give back a number that represents it in a mostly unique way. Okay? And we'll talk about what makes a good hash code later. Okay? So hopefully I've convinced you there's a cheating way of doing sets that involves turning your data magically into a number and then setting values to true or checking if they're true. And we just need to resolve these two issues and we have something real. Okay. All right, any questions before we move on? Okay, cool. I have a hat to give away, I think, assuming I brought it. So RailWorks is North America's leader in track and transit systems construction and maintenance services. All right, how much to do the hat throw? Oh, it didn't go very far. Uh-oh, okay. I thought the hat would go further. If you don't really want, oh, it's yours now. Okay. My nephew works at RailWorks, so I'll have one additional RailWorks hat. So if you missed it, I'll try and throw better this next time. All right, handling collisions. So the biggest array in Java is 2 billion entries. That's as big as you can get. And the pigeonhole principle, which is a very lovely mathematical notion, very simple. Okay, here there are 9 boxes and 10 pigeons. There's no way that each pigeon can have its own box. That's all the pigeonhole principle is, right? If you have 10 things and 9 boxes, that's more things than boxes. So if there are more than 2 billion possible items, then there have to be items that share the same box. So if we're going to use an array of integers, we already know there's going to be guaranteed collisions, no matter how clever we are. For example, let's say planets, right? If you said, I can fix the problem, Josh, I'm going to make there be no collisions, well, I tell you that's impossible, because a planet, for example, has a mass, an x position, a y position, an x velocity, a y velocity, an image name. And if you think about all the combinations that are possible, there's more than 2 billion combinations. So there's guaranteed going to be 2 planets that get the same magic number. Okay? Actually, just strings alone. There's more than 2 billion possible strings, right? We got 1, we have 2, we have all the others, we have 4 billion and 6. And I've proven to you there are more than 2 billion strings. Okay? So first of all, you have to deal with it. There's no way to just punt and say, I'll come up with a better magic number function. Okay? All right? Well, how do we deal with it? Well, one way is, suppose we have n items that have the same magic number, which from this moment on, I said it out loud, but from this moment on, I'm going to call it the hash code. So instead of storing true, instead of true or false, we're just going to store a list of the items at that position. Okay? So instead of just saying, yes, cat is here, I'm going to say in position 3,284 or whatever, cat is here. And that addresses your problem, which was how do we get the number back? We're going to actually store a reference to what had that hash code. So how do we implement the list? Well, the easiest way is with a linked list, but you could use an array list, or you could actually use a set of some kind. But the point is that instead of having true-false values, we're going to have buckets, right? Some kind of storage unit where we can put things, okay? So the most common approach is this. It's called external chaining or sometimes separate chaining. And so whenever somebody says insert cat, we go to position 3,124. How do we know to get to this position? It's our hash code. We have a magic function that says cat is 3,124, and we write it down. We say cat. Okay, suppose we insert potato, rotato, and totato, where we used to say, okay, we're going to have to tolerate ambiguity. Here we say, no, we have a list of all the things that you inserted that had that number, okay? And so then, again, that's how you get back your number. Like if you want to know what's in the set, well, now you don't have to have a function that goes backwards. You don't have to go from from this number back to totato. And in fact, obviously it's impossible because there are multiple things that get the same number. You can't have a function that goes backwards. It's actually physically impossible. So that's our tweak. Now, actually, that's pretty much all there is to it. There's a little more, but the point here is that this lets us address collisions in a really simple way. Is it fast? We'll get there. But certainly I hope you agree that if we think of Q as the length of the longest list, a contains operation on this data structure will be theta Q in the worst case. So some of the lists might be really long. Maybe there's a ton of things that people inserted that all just by bad luck happen to be hash code 55 million or whatever. 55 million something. Maybe that happens. And so in that case, your runtime would be Q. But what I'm going to show you is that you can keep Q small by being clever. If you have an array, and like each of these items is itself an array? Oh, so could you, instead of using a list, use something else? Sure. But what I'm going to show you is that a list is good enough. Okay? So you might be tempted to say, well, I don't like a list. You already talked about binary search trees. Why isn't this a binary search tree? That's a valid data structure, but I'm going to convince you that lists are simple and actually fast enough. Okay? All right. Now, why is insert q and not 1? This is kind of a little tiny question. It might seem like insert should be really easy because you just stick the item at the front. Why would you need to be q? Why is insert any slower? Yeah. Yeah, you don't want to have duplicates. So if you insert totato again, you should really look in this list and make sure totato's not there. Yeah. The ordering of the chains is not important. So you could counter-argue and say, well, whatever, sure, just stick it at the front, and if there's multiple copies, who cares? That's a valid argument, but I like this a little better aesthetically. Yeah. Ah, that was his point. Yeah. So could you do something more complicated than have a list, like do a hash table or a binary search tree or something? Yeah. But I'm going to show you that this is good enough. All right. So the key is, you might not like q. Can we make q better? Yeah. But I'm going to show you that you can keep q constant in a clever way. All right. Now, another really important observation is, guess what? We don't need 2 billion buckets, right? Seems kind of impractical if every time you want to make a hash map in Java, you have to use 2 gigabytes of RAM. Good news, I have a solution. Let's suppose instead of having a couple billion elements, we just have 10. If we use these 10 buckets on the right, where do you think the item should go? Give me some mnemonic. What do you think? Where would cat go? 4. 4 seems good. Or 3, I guess. But I'm going to pick 4. I could use the bottom digit. So I could say, okay, let's just mod everything by 10. That's the most natural, easiest thing to do. In that case, potato, rotato, and totato all end up together in bucket number 1. So bucket is just like whatever the list is, however you're storing your buckets. I'm doing list-based buckets. 3 is dog, 4 is cat, and 7 is snack. Okay. So good. All right. Any questions about this approach? So we're getting closer and closer to something that's real. Yeah. Yeah, so the idea was, if you mod, doesn't it increase the likelihood that they somehow end up in the same set? In this case, they were all separate. But of course, there's a way bigger chance. So if I have 44 and 24, they'd be separate over here. But in this case, they would both end up at bin 4, and that's true. So the fewer the buckets you have, the bigger the more collisions you have. Yeah. So why was the hash code useful since we're just going to throw away everything other than 10? Well, we'll see. So you could say, shouldn't the hash code just return a number that's between 0 and 9, for example? That would be fine, except we'll see that the number of buckets can vary. Okay, so that's the key. Yeah. So would a base here that's not 10 be better, like something that's prime? Yes, but for reasons we haven't discussed and may not. Yeah. All right. But this at least works. And maybe there's some numerical properties that are not as good. Okay. So how about the performance of this thing? Well, we know the worst case was q, where q is the length of the longest list. But let's talk for a moment about the average runtime. So the runtime of operations is a little messy in this case. It depends on the number of items that are in each bucket. Okay? So if we have n items, and they have m buckets, the average runtime is going to be, totally on average, is going to be over tons of operations across all over the hash table. It's going to be based on L, which is just n over m. And we call that the load factor. So the average runtime of each operation will be L. And so in this case, I have 11 items and 6 buckets. So on average, a contains operation will take 1.83 compares. And if I do another insert, it'll be close to that. Okay? So what I'll note is that if L is small, our data structure is going to be very fast as long as things are nicely distributed. So if things are nicely distributed and we have a small L, then the average runtime will be very fast. So here's a question for you. Not worrying too much about distribution. Let's just assume that things get randomly distributed pretty well. As n grows, what can we do to make sure that L stays small? So as we add more and more items, right, this list is going to get more and more stuff. What can we do to make sure that L stays small? We could delete items. That's not a very good solution. So what else could we do? Yeah. Yeah, we get more buckets. So we could say double the size of the array. Okay, so in that case, let's try it out. Or increase it in some way. So here I have some item. They're just like Minecraft images I grabbed from the internet. Here's an axe, and let's say its hash code is 16. Why? I don't know. Well, who can say what any hash code comes from? Who cares? This helmet is 13, the apple 7, this bow is 20. Okay, now if you take these items, in this case the load factor is 1, and maybe we don't like 1. We want the load factor to always be lower, so we resize it, in this case, to 6 items. So my question for you now is, which bin does the apple land in after resizing? And I'll give you guys a minute to think about that. Oh, it should be yellkey.com, by the way. I don't know why it picks skin, which is a weird word. It just feels, I don't know. I have a slight aversion to that particular yellkey, but hey. But the next one's a weird one to go with it. I didn't really tell you how to do this. I'm kind of letting you trust your intuition about what feels right. Okay. All right. Okay, so the hash code of the apple is 7, and so we need to think, where should it go in this array? So what did we do before? We modded by 10. In this case, what does it seem like we should mod by? 6. Okay. So it turns out that 7 mod 6 is 1, and you can think about it this way if you don't want to think about it too hard. It's 0, 1, 2, 3, 4, 5, 6, 7. That's where apple lives. All right. Any complaints? Yeah. Yeah, doesn't it seem like resizing may be slow, right? Yeah, it could be complex. It could be done in theta n time, though. So resizing is slow, but it doesn't happen often. Yeah? Other thoughts? Yeah. A number base 6. Like modding by something else, you mean? I think 6 is the right thing to mod by. One, 2, and base 6. Oh, I see what you're saying. You converted it into base 6 and then took the bottom digit. A first digit. I don't know what that is. It's some other operation. It might be useful too. I'm not sure. Good question. I think it's simplest just to mod by the number of buckets, though. So in this case, Apple ends up here. And I'll notice something really important. Apple used to live alone, right? No friends, living like a really comfortable life. Now you have a roommate, this helmet. All right, that's how it goes. And Bo used to have Axe as a friend. Now they're separate. So the point here is that resizing is a complicated operation. It's not, you get some new buckets, you're done. Everything can move, okay? But that's okay. Here's another question for you. Let's suppose this apple here, let's hash code is -1. Philosophically, where do you think it should go? Just, I don't know. I'll let you guys think about it. So this is kind of your call. But I think there's a right answer, but maybe you don't. So if skin wasn't good enough for you, now you have medical. These are randomly chosen. Okay. So we toss this golden apple in, and what happens? Well, I think 3 is a better answer, and here's my argument. All right. So if something had hash code 3, it should be in the third bucket. Hash code 2, second bucket. Hash code 1, first bucket, hash code 0, 0th bucket, and then we roll back around for -1. So I think it's a little more natural. So that's the approach I'm going to use. But maybe you disagree. That's fine. So I'll make a quick note. Whenever you do the lab for this week, you'll get a chance to write insert. And if you do -1 mod 4, you don't actually get this answer, like the natural modulus. Instead, what you'll get is just -1 again. So Java's % operator isn't quite the same thing as this natural, group theoretic feeling like you go in a circle. It also feels right. This is just, it feels a little wrong. So what you could do instead is use math.floormod, and this will work well. Okay? So just be aware. There's a little bit of a difference between your intuitive sense, if you agreed with me intuitively, and what % does. So there you go. That's one way to resolve it. All right. Great. Okay, so now let's talk about hash tables. Now we have defined everything we need to know, and now I can tell you what they are. So this data structure that we've just designed, all this work we've done, is called a hash table. And it's kind of wonderful because it relies on what was originally just a stupid hack. Like, okay, we'll just make an array and make a bunch of true falses, and we revise that into something that's real. So what happens is that every item you create, and those items could be integers, they could be strings, they could be pictures, they could be anything, they get mapped to a bucket number using a hash function. And this hash function is just arbitrary. Someone writes it, it gives you back a number. So computing the hash function consists of 2 steps. It's a little terminology here. First, you compute the hash code. So the hash code is, I have a TE tile, I get a hash code back. I have a map that I built for my game. It's also represented by some number. Who knows what? And that's some integer in the range of possible Java integers, between -2 to the 31st and 2 to the 31st minus 1. This just happens to be what integers in Java are valid. The next thing you do is you compute the index by taking the hash code and modding it by m. And by mod here, I mean the intuitive handles negative numbers gracefully version. So this whole thing is called a hash function. It's hash code, then mod. Okay? The next part that was important was if L, which is our load factor, gets too big, we increase M. Typically by doubling, but you could do some other geometric resizing. Now, if multiple items map to the same bucket, we have to resolve the ambiguity somehow. There's 2 common techniques. One is external chaining, which is making a list, which is what we just did. And there's another version called open addressing, and that'll be in the extra slides. And there's actually more versions of it. There's like cuckoo hashing, and there's a whole field of research which was just weird ways of dealing with ambiguity where we have collisions. But it turns out that this list approach is pretty good, right? Because the average time for each operation is just going to be n over m. And if we resize strategically so that the average list is of a constant length, then the list will all be on average of constant length, and the runtime will be very fast. Okay? So there you have it. Now, open addressing I just mentioned because it might occasionally come up at job interviews. Maybe it's a thing that happens. So for those of you who go do, Google interviews or something, you can impress somebody by also knowing about that, even though we won't talk about it. Okay, so that's hash tables. Now you know what they are, and they're cool. All right, any questions about this? We have a little more to do, but that's the hash table. Yeah. Overlap of 13. Sorry, say again? So we covered the collision issue because we just make a list of everything that's equal. Now, we're saying not everything that's equal, everything that has the same hash code. So we got that taken care of. Yeah. Yeah. So why is a linked list better than the binary search tree? It's not obvious that it is. I think what you need to do, if you want to know which one's faster, you'd have to do some kind of profiling where you write code and run it, see which one's faster. Now, the search trees are going to be really small. Like maybe if you keep your load factor below 10, those search trees will only be 10 items. So it may be that the overhead of building it's not worth it. Maybe it is. It's not going to be much different, though, because the trees, it'll be like, is the runtime on average theta q? Is the runtime theta q or is the runtime theta log q? But if q is really small, the difference between q and log q is effectively nothing. Yeah. What's that? Oh, and also, yeah, I guess the point was brought up that your items have to be comparable to be stored in a tree. So maybe you have pictures and there's no way to compare them. All right. Now, there was an important point implicit to all this, which is that I was assuming the items were nicely spread out. That is, they're not all in one bucket, right? So I'm assuming that for a bunch of items, it feels bushy, basically. So we saw before that a balanced binary search tree has log n time for its operations. And if we have nice distributions, if we have external chaining, that was just my name for having lists, and each list is of, we have a fixed size, that is we only ever have a certain number of buckets, the contains and insert operations will be theta L on average, where L is the length of the lists. If we do resizing, it's still theta L, but what's the difference between these two here? So it seems like the runtimes are the same, but what's different about L? So if you have a fixed size, L is just going to grow and grow and grow as you add items, but if you resize, since L is the ratio of n to m, and m increases with n, L will stay constant. So in other words, if we have no change, we don't do resizing, the load factor is theta n, but if we do resizing, it should be theta 1. So this is the cheat that lets us get runtime that's theta 1. Okay? So we actually are faster than a balanced binary search tree because we're building more buckets on demand. As people keep adding things to our hash table, the hash table gets bigger, everything stays constant time on average, assuming things are spread out nicely. Now this is also an amortized time because some operations are going to take longer because we have to do what? Resize. But resizing happens only every so often. We have the whole Grigameth's earn, hey, yada, yada, yada from before. Same argument, ends up being pretty fast. So there's one last little detail, which is, of course, that the performance depends on how many things are in each bucket. So our load factor is n over m, and the average runtime is theta of L, where L is the length of the list, but average obviously isn't the whole story. We actually want balanced buckets. If we have a list that's super long, it's true that the average, that the load factor is maybe constant, but what's going to end up ultimately happening in this case is that since everything's in one bucket, the operations will be slow. So this is kind of like keeping bushiness in a binary search tree. We don't want all of our items to end up in one bucket. We want them to be spread out ideally. But unlike a binary search tree where we have to do all this isometry business to make things bushy, it's conceptually much easier to solve such that we can fit it at the end of lecture, which is our little bit on hash functions. Okay? So in general, we want hash tables where things are spread out. And it's not really the hash table's job to make sure that's the case. It's actually the hash code's job, because the hash code tells you where it's going to go. So I'll give you an example of a bad hash code function. Return 0. So it technically works. It gives you a bucket to go in. You always go in that bucket. But it's going to mean your hash table is really, really slow. It turns out that our convert to int function for strings was also bad, because as you know, we threw away the top bits. Potato and give me a potato have the same hash code. So it's possible to create, even though our hash table can handle it, like, so you insert potato, rotato, totato, similar, you end up getting a really long list. Everything's in that one list. So we want a better hash code method than what we did, this convert to int. And it turns out to be pretty tricky, and writing a good hash code function is hard. So the convert to int function that we did, you could write it out this way. I mean, this is like an alternate way of describing what we did with cat. So we take our top digit, we subtract out a and add 1. This is how we take a letter and turn it into a number. If this doesn't quite make sense to you, imagine that if you give the letter C to this, you get back 3. That's all it means. We then multiply by 32 to some power, then we add the next letter, and so forth. And the problem is that, well, first of all, it was intended for lowercase only, which was weird, but simple. And also the top bits were ignored. So we want to fix these issues for our convert to int function. So one thing we could do is get rid of the lowercase strings only by removing this whole minus a business, and just take whatever the raw character is. If it's an equal sign or whatever else, we'll just multiply it by the power of 32. But we still, in this case, we have the issue that we are going to lose all of the bits at the top. Okay? So how do we deal with that? Well, instead of doing 32, let's do 31. Seems like a pretty tiny change. And the reason this works is a little tricky, but we'll see in a moment. But basically, the big picture is that in convert to int before, we tried to make each character correspond to specific bits. We said the last letter, T in cat, that should be the last bits, and A should be the next bits, and C should be the next bits. But that was actually totally the wrong approach. We want the opposite to happen. We actually want to do something a little messier. Okay? So while it was great for understanding what was going on in lecture, maybe, 31's better. So let's look at what the 31 process looks like. So if instead of multiplying by 32, we multiply by 31, we'll get a different hash code. So let's take cat. Okay, so before, with our old convert to int function, C was this, A was this, T was this, we ended up with 3,000, whatever it was. Okay. Well, in this alternate approach, I'm going to multiply instead of by 32 squared, which is the same thing as shifting over by 10. The letter C is going to end up being this number, which is 95,139. So the letter C is represented by all these bits. So the important point, if you've kind of lost the thread for a moment, because it feels like lecture's almost over and may as well like get on, think about what's going on in 5 minutes. Let me bring you back. So before the letter C was these 5 bits exactly. Now the letter C is all of these bits. It's a big old messy pile of bits. How about A? Well, the letter A is this sequence of 16 bits. Why? Because at some point in the 70s, I think it was, someone decided that A is this number. So A times 31 gives us 3007. And then here's T. So T is represented by these bits. So in other words, C, A, and T are all contributing to these lower bits. And when we add them all together, we end up with this number at the bottom, which is 98,262. Different than what we had before when we used our base 32. Okay? So again, the most important point on this slide is that the letter C is represented by a giant pile of bits instead of just 5, and those get intermingled with the A bits, which brings together this notion of why it's called a hash table. Okay? I have a note there I'm not going to say anything about, but the point here is that, I don't know, have you made hash browns? Anybody who's made a hash brown here before? Okay, a few people. So you don't take a potato and like cut it into perfectly neat slices and then like make sure the order's all arranged so that when someone eats their food, they can know exactly what part of the potato was, right? Instead, you like just dice it up and go crazy and mix everything all up. That's why it's a hash table, right? So hash browns are all about taking your potato and just disintegrating it and smearing its information all over the place. Same deal here. Cat, right? The letter C, just like, there, it explodes into all these bits. A, all these bits. T, all these bits. And then, for good measure, after you blended them each individually, you add them all together. And it tastes delicious. Okay. So how do you hash? So that's all that is to hashing. Now you can actually hash more complicated objects, right? So for example, let's say we want to do the hash code of a collection. Well, then you just say for every object in my collection and me, I'm going to compute the hash code individually and then scramble those together and add them. So I compute the hash code of each individual object and do the same trick with 31. Okay? And you could save time by only hashing the first few items, up to you, but then you'll have a higher chance of collisions. You can even hash recursive data structures. How would that work? Well, we hash the current thing. Actually, sorry. If the current thing's null, the hash code's 0. Otherwise, what we'll do is the current thing, we'll hash it, and then we'll hash the left, hash the right, and then mix them all up. Again, with this power of 31 trickery. Okay? And what's neat about hash codes, and again, because the hash table is such a fundamental data structure for implementing sets and maps, you have to do it for everything in Java. Now, you guys have made classes, right, where you did not create a hash code, like Planet or ArrayDeck or anything else, right? Nonetheless, there still was a hash code function, and it was inherited from the object class. And by default, you just return the address of the current object, and it works generally, but it's not ideal. Now, you can override it yourself. And in fact, in IntelliJ, there's a function where you can say generate hash code, and it'll come up with a good one for you. So hash tables, again, they're so important that Java, in the language, there's only like 5 things you have to do for each type that you build, and one of them is making a hash code function, ideally. Okay? So to round out, Java gives you a hash table, hash table-based implementation of sets and maps that are called hash set and hash map. It's basically just what we did in lecture with a couple little tweaks. Now, I want to give you a couple little admonitions. One is you should never store mutable objects in a hash set. See the study guide problems for why, but there's a really good reason. And 2, you should never override equals without overriding hash code. So if you override equals without hash code, you can run into trouble. Study guide will give you a reason why. So in this week's lab, you'll get a chance to do hash maps and BST maps. That's it. So I'll leave the summary slide up. Thanks, everybody. Got to bail quickly. And, see you next time.